In this video, I'm going to go through an entire force method example for a frame shown here, where we choose the moment reaction at C as the redundant. So as you see here, we have a simple frame, ABC. The frame has a uniform load of 25 kilonewtons per meter on member AB, and we are asked to find the moment diagram, and this is a constant EI section. So the first step is to select our redundant. The redundant is the restraint that we're going to remove in order to make our indeterminate structure here, which is indeterminate to 1 degree, into a determinate structure. And then we're going to use a compatibility condition in order to find our redundant reaction force. So the easiest redundant to select for this problem would probably be the vertical reaction at AY, because that would turn this whole frame into a fairly simple cantilever problem. But in the interest of doing something a little bit more difficult to show the process, let's select MC, which is our moment reaction at point C. So if we remove MC as a restraint, then C is going to turn from a fixed end into a pinned end. So we're going to be working with a compatibility condition such that the rotation caused at C due to the external loads plus the rotation caused at C by our redundant, we're replacing the restraint, the moment restraint at C by a point moment at C, is going to be equal to 0. So basically our external load causes some rotation about C, causing this to change direction, and our redundant is going to bring that back to its original location here, because our compatibility condition is that we have to have this initial rotation to be fixed at the end, at end C. So let's draw our primary structure, which is the structure with the redundant reaction removed. So this is now our structure without the redundant. So you see we're left with 3 reactions, AY, CY, and CX. So MC as a reaction is gone. This is our primary structure, which is a determinate structure where we can solve everything, including all the rotations and displacements and the internal forces, using nothing but equilibrium. So the first step is that we're going to apply our external load to this primary structure, okay, which is 25 kilonewtons per meter. And then we're going to determine how this structure deflects, and it's going to deflect something like this and like this. There, that's a little better. So once this structure deflects, there's going to be some rotation here. This is the tangent of this blue line, okay, at C. And we're going to have some rotation here, and this we're going to call theta C naught. And this is the rotation that we're going to zero out when we apply our redundant moment at this location to the primary structure. So this is our primary structure with the external loading applied. And we're going to use this structure to find theta C naught. So in order to find theta C naught, the first step, we're going to start this as if it was any basic structural analysis problem for a determinate system. So we're going to find the moment diagram, and then for this particular problem we're going to use virtual work in order to find this rotation. So first let's find the reaction. And we do that simply using equilibrium, some fx, some m about point A, and then some fy. I should label, this is A, B, and C, if you recall. And then using these reactions and doing our regular moment analysis, we're going to come up with a shear force diagram and a moment diagram, and those are going to look like this. So this is a relatively simple moment diagram based on these forces. So we have a vertical reaction here, then we have a distributed load causing a change in shear that's linear, then this is the shear at B. That shear changes around the corner because of the change in direction, so we have 25.7 instead of 42.6. And then our moment diagram simply looks like this, with a parabola between A and B and a triangle between B and C. And you can try this out by yourself to try to confirm for yourself that these are correct. Now this is quite a complicated moment diagram. for virtual work because we have a simple parabola over here, which is fine if this was 1. But then we have a kind of parabola plus a rectangle for 2 and 3 here, and then we have a simple triangle here for 4. So anything in here is going to be kind of difficult. So I'm going to do this in 2 different ways to show you the 2 different ways to solve this virtual work problem. The first way, we're going to actually find the equations for M and for the moment for AB and BC, and do a manual integration that way to find the integration of the product of the real and virtual system. Of course, we haven't got to the virtual system yet. And then the other way I'll show you, which is a little bit easier, is how to do this with the table. But again, it's a little bit complicated to do this with your integration table because we have 2 different shapes here to the right of the 229.6. So first, let's find the moment of these. So I'm going to call this one x1, and then I'm going to have another x direction x2. So for this shape, we'll call this overall shape 1, okay, for this analysis. We'll call this, let's just call it shape 4, because this one is 4. So this one's going to be 1, this one's going to be 4, and we're going to find the moments for these. So for the first parabola here, we know that the equation for a parabola, so moments, we know that the equation for a parabola is y equals ax squared plus bx plus c. So what we have to do here is to apply boundary conditions and different points on the parabola in order to solve for this. So we'll need 3 different points on the parabola in order to solve for a, b, and c. And I'll leave this up to you. One of them is obviously going to be x equals 0, y equals 0. Then the other one that I chose is x equals 4.286 and y equals 229.6, and the last one is x equals 6.0 and y equals 192.9. So these are actually all of the points on the parabola that I've already determined, and there are 3 of them. So using those, we're going to find first that c equals 0, a equals negative 12.5, and b equals 107.15. So to find a and b, you have to solve a system of 2 simultaneous equations. Let's fix this here. 4.286. And then so we're going to find, therefore, that m1 is equal to negative 12.5 x squared plus 107.15. So this is x1 squared, x1. So this is for 1, and then for 4, which is a simple triangle, this is quite easy. We know that the equation of that triangle is going to be 192.9, which is the peak at x2 equals 0, minus 25.72 x2. So we're going to use these moments when we do our internal virtual work calculation. But first, we need to find the virtual system. And this is what our virtual system looks like. So we start with our primary system again, which is our frame with the 3 unknown reactions, vertical AY, vertical CY, and horizontal CX. And then we're going to apply a unit moment rotation at the rotation that we want to find at the location where we want to find the rotation. So you recall, this is our system for the external load. Okay, so we have our external load system, and then we're trying to find this rotation. So you remember, for virtual work, in our real system, we apply the real forces, and we find the real internal deformations, which in the case of a frame are in terms of beam curvatures. And then for our virtual system, we're going to apply a virtual unit load, which is a virtual external force, onto our structure at the location and in the direction of the deformation quantity that we want to find. So in this case, we want to find a rotation theta c naught at point C. So that means at point C, we have to apply a unit moment. which is what we've done down here on our virtual system. So I've applied a positive unit moment in the counterclockwise direction, and now with this system we're going to find our reactions. So these are our reactions using our equilibrium. And then we can also find the shear and moment diagrams, which look like this. So you can see that in the shear diagram we have constant shear in AB and BC. The shear changes magnitude around the corner because of the direction, so this is the cos of the angle. And then the moment has a triangle on AB and a trapezoid on BC. So this is fairly simple. Again, you can confirm this for yourself. So again, since I'm going to do it both ways, I'm going to have to find these moments in terms of the same x quantities. So I'm finding equations for the moments for AB and BC. So we'll call this one 1 again. We'll call this one 4 again, since we had 2 and 3 on the previous one. So we have x1 and x2. So our moments, and these are just triangles, so they're quite a bit easier than the parabola. They look like this. And we get two equations, one in terms of x1 and one in terms of x2. And then we can use these equations to find the deformation using virtual work. So recall that virtual work, we have the external virtual work equals the internal virtual work. In this case, our external virtual work is the real external deformation, which is what we're trying to find, times the virtual external load, and this is the unit load that we applied to our virtual system, equals, this now equals the integration of the virtual moment, which is the virtual internal force, times the real curvature, which is our real internal deformation, dx. Okay, so these ones I've labeled mv because those are our virtual moments, and the previous ones I just labeled them m because these are the real moments, and we divide the m by ei to get the curvature. So then we can solve this equation. So here are some intermediate steps. So we have to do this integration for each separate member. So here's the first member, which is 6 meters long, and we have the virtual moment times the real moment, and we're going to integrate that product. And then on the second member is 7.5 meters long, and we have the virtual moment and the real moment, and we're going to integrate that product. So these numbers down here show the product of mv1 and m1, and you can try that out for yourself. So it's this value times this value up here. Okay, so this is just laying it all out before integration, so these are both the products of these two. So if you carry out that integration, you get these expressions, which are evaluated at 0 and 6, and this expression for 0 and 7.5, and we work that out and we get these numbers, and then we divide all of that by our unit moment, 1 kilonewton meters, and then we get 865.1 kilonewton meters squared divided by EI, and the units of EI are built into EI. So these units come from moment times x, so that's kilonewton meter times meter, so that's kilonewton squared meters cubed, and then we divide that by 1 kilonewton meter, so we get kilonewtons single meter squared. So then there's an alternate method to do the virtual work, and it works out like this. We're going to use the integration table, and the integration table looks something like this. So you probably have seen something like this before. Okay, so you have your one shape for the real system and one shape for the virtual system, and these are all the integration for the products of the two shapes. So if we go back to our system, it's a little bit complicated. So our first shape here is a parabola, and you'll notice in this table the parabolas always have to have a slope of 0 at one end. So we can't just take this entire parabola here between A and B. We actually have to split it. So we have one parabola, which is labeled number 1 here. Then we have which goes from 0 to a slope of 0. And then we have another parabola, which is labeled number 3 here, which goes from a slope of 0 to the end. And then the last part here, which we have to separate out, is a rectangle, because we don't have any parabola here that has a height at the end. It always has to end up at 0. So we have to split this up. And so for this first part, we do this parabola number 1. So let's look at the first one. So we're going to have this parabola with a 0 slope times this triangle only up to the location of the maximum point on the parabola for the real system moment diagram. And then for the other two parts, we have to do the parabola here, which is the small piece, times the entire trapezoid on the virtual system, plus the rectangular piece here times the entire trapezoid. So this is like the situation. So we're doing an integration of a product of two different moments. So it's as if, so for the real system, remember we have like moment 2 plus moment 3, and for the virtual system we have only this, so let's call that MV2. Okay, and so if we want to find the integration for the product of these two, okay, the product is M2 plus M3 times MV2. So if we expand that out, that's M2 times MV2 plus M3 times MV2. So for each piece that you break up the real moment diagram here, you have to multiply that by the entirety of this trapezoid. So if we want to look at doing that, we're looking to find our internal virtual work. The first piece is the large parabola times the triangle, and the triangle is only up to this point, and this is equivalent to the same point on this parabola where it hits the max, so that's 4.286 from the left. So this is 4.286. Then using similar triangles, we know that this is 0.408 high. So we have our parabola, which the maximum is 229.6. The length here is 4.286, and the height of this triangle is 0.408. Then we have the small parabola. Okay, and the height of that small parabola is the difference between 229.6 and 192.9. Okay, so that equals 36.7, and the width of this is 1.714, and we multiply that by the entire trapezoid for the virtual system, which is 408 on the left and 5712 on the right. 408 and 0.5712. And then plus, we have a rectangle. Okay, so now this is the small rectangle here below, and that's going to be multiplied by the entire trapezoid again. And the rectangle is 192.9, and the length again is 1.714, and then 0.408 on the left and 0.5712 on the right. So you see we have now two internal virtual work products that are associated with the location between this point and this point. Okay, and then the last part is very easy because it's just a triangle that looks like this times the same trapezoid. And that looks like this. So now that we have the geometry for all of these, we can look at our table. So for the first one, we have a parabola that is high on the right times the triangle. So we go here, we find the parabola times, here's the triangle. So we find the value for the integration of that product is 5 LMQ over 12. So here we say 5 LMQ over 12, and then we do that for the rest of these shapes as well. And so here I have the value of the integral of the product equation above what we're integrating for here. So there's 4 terms. And if we work all those out with the geometries that I've set there, we get 167.3. And I forgot here that this has to be 1 over EI times all of these. Okay, so this is all of this divided by EI. And then we get 865.5 over EI for internal virtual work. And you'll see that this value is very similar to the value that we got for the internal virtual work when we did it the integration way, the full numerical integration way. We're off by 0.4, which would be from a round-off error. So all of that crazy work is just so that we can get this rotation of our primary structure with the external load applied. So we have now theta C naught. And so theta C naught we found right here is 865.1 kilonewton meters squared over EI. So now we have to find the same rotation in the same location for our primary structure, but this time without the external load and just with the redundant. Okay, so since we've probably forgotten, here's what our real system looks like. So this is our primary structure. Okay, so this is the structure for which we've already removed the redundant reaction. So it looks like this. So this you recall. So this is our primary structure. We don't have a moment here because we've released the fixed end. So remember, our original structure had a fixed end at C, and we chose moment at C as our redundant, so we removed the moment fixity there, and we're left just with a pin and a roller, and this is a determinate structure. So now for this real system, we need to find what value of the redundant force, which is a moment, will turn basically the end of our structure back to where it's supposed to be. So at C, we have a rotation caused by the external, okay, but we know that this rotation in reality has to be 0 because it's fixed. So what we do is we apply a redundant moment at C, okay, and we see how much redundant moment we have to apply at that location in order to bring this rotation back to 0, which we knew it's supposed to be. And the value of that moment that causes this rotation to come back to 0 is equal to the moment reaction at point C. So we're going to apply that redundant as a unit load, and that will give us how much rotation we'll get at C for a given value of moment, okay? And then we're going to basically end up with a deformed shape, which looks something like this. And again, this is going to cause some sort of rotation. And now generally this is a rotation, right? A rotation, CC. Okay, but we're only doing it for 1 kilonewton, so we're going to call that instead a flexibility, CC. You remember, flexibility is equal to the deformation divided by a load, or a moment, for example. So this would be a rotational flexibility. We would be talking about a rotation divided by a moment. Okay, so if that moment is equal to a unit moment, which is 1 here, okay, then the flexibility is equal to the rotation deformation. Okay, so we're going to find the rotation here, which is due to the 1.0 moment, and that rotation is equal to our flexibility. And then later, we can back calculate for a moment, which is equal to a flexibility divided by a rotation. Here we're going to put our real rotation due to external load, right, which is what we want to cancel out with our redundant. And since we know the flexibility, we can find what kind of moment we need, what kind of redundant moment we need in order to balance out that original rotation B naught. Okay, so we now have our real system for finding the flexibility due to the redundant. And you might notice that this system looks very familiar because we just dealt with a very similar system, in fact an identical system, which was the virtual system that we used to find the rotation due to the external load. Okay, and this is always the case because our redundant is in the same location and direction as the rotation that we're trying to find. So this system, as I said, happens to be the exact same as the virtual system for the previous primary structure when we applied the external loads. And the good thing about that is it saves us a lot of work because we've already found the moment diagram for this exact system with a unit moment at point C. Now, so if we want to find this rotation, FCC, and we want to use virtual work, we have a real system, and this is our real system. But then we also need a virtual system, right? And you'll recall that our virtual system, we have to apply a unit load or a unit moment at the location and in the direction of the rotation that we want to find. So here we want to find a rotation about C, which means we have to apply a unit moment at C in order to find that. So our virtual system, okay, if we're going to start with our primary structure again, our virtual system to find this FCC is that we have to apply a unit moment at point C. And this again happens to be the same as the real system. Which is great because again it saves us a lot of work. So now we actually have three systems which are the same. The real and virtual systems for finding the effect of the redundant, and the virtual system for finding the effect of the external load. These are all the same, and they all have this same moment diagram here. And this is always the case when we do these kind of analyses, where we're using the force method, and we're using that in conjunction with virtual work. So these two methods really kind of are natural to go hand in hand. So if I want to draw the moment diagrams for the real and virtual system again, then we know that it looks like this, which is exactly the same as the virtual system for when we applied our external unit, our external real loading to the primary system. So this is the exact same system, which I've copied here. And the virtual moment is the same as the real moment. So this is the same for both systems. So now we can do our virtual work, internal. And again, so now this time we're going to have a triangle times a triangle, because the same on both, and a trapezoid times a trapezoid. And so we can look at our table, triangle times triangle, right, is equal to LMQ over 3, and trapezoid times trapezoid is this equation down here. So let's fill that in. And if we do that, we get that the internal virtual work is 5.397 divided by EI. Then we equate the external virtual work to the internal virtual work, where our external virtual work is the external real deformation, which is this flexibility term, right, because we're talking about a unit moment, times the external virtual force, which is 1.0 here, equals our internal virtual work, which is 5.397 divided by EI. So then FCC, which is our flexibility, is equal to 5.397 kilonewtons squared meters cubed divided by EI. Because in this case, this unit moment that we're applying is actually unitless. So then we know that our total deformation, okay, is equal to the flexibility times the applied moment. Okay, so if we look back at our compatibility condition, we remember that we're trying to balance out the rotation that's caused by the external load plus the rotation that's caused by the redundant. And those have to together equal 0 because we know that there's no rotation allowed at the fixed end. And so we can rewrite this as FCC, which is our flexibility, times the MC equals 0. Recall, right, that our flexibility is equal to the deformation, or the rotation in this case, which is FCC divided by our moment. So this is how much deformation do you get for each unit of moment. And if we sub in all these values, we get that MC is equal to 160.3 kilonewton meters. And so all of that work that we did was basically to determine one of our reaction components. So we released the moment reaction here, and we went through all of those steps, finding the rotation due to the external load, finding the equivalent rotation due to the redundant that we removed, just in order to find the moment reaction at C. And now we've done that. So now that we've found one of the moment reactions, we only have 3 left. So it's easy enough using equilibrium to find all of the rest of the system. Okay, so we got a negative moment up here. So that means it's in the opposite direction to what we drew it. So we were always drawing our redundant moment counterclockwise, so the moment is actually clockwise. So now we have this situation. This is our real original system, 25 kilonewtons per meter. We've solved for one of the reactions, which is the moment reaction here. We found that's 160.3. So now we can go ahead and find the rest of the reaction. And so using the equations of equilibrium, we find AY, CY, and CX. And then knowing all of those, we can draw our shear and moment diagrams for the real system, which look like this. So we have a shear diagram that looks like this. So that's our AY now. And then this slope is defined by the distributed load. And you see we have a change in shear around the corner due to the change in direction. And then these converts into our moment diagram, which looks like this, where now we have, this is 101.7 as well around the corner. We have a compatible corner, notice. And then at the base here is our moment reaction, 160.1, which was what we solved for. 160.1 is due to a rounding error. 160.3, which is what we solved for using our compatibility criterion, which makes sense. And so that is how you find the moment diagram of an indeterminate system, which is indeterminate to 1 degree in a frame using the moment reaction as a redundant.